Okay, so I've started the recording. So good morning to all of you attending the class. Um, One thing that I will announce is I will roll out the second assignment. So I intend to give 4 assignments overall, 2 before the mid-semester and 2 after the mid-semester. So the 4 assignments combined with the mid-semester and end-semester tests in whatever best possible way I can conduct the tests will consist of your overall grading of the subject. So with that, okay, so let's proceed. So last 2 days, right, we are trying to, from the basic physics, right, without getting into a domain which is beyond the scope of the subject, we have been trying to derive what sort of the aspects like the particle velocity, the particle displacement, or the pressure in the fluid or in the medium of sound propagation, how these quantities vary as a function of time as well as a function of space, right? So time is t and space, we are talking of unidirectional wave propagation. So we are talking of only one direction here, x. So we try to derive based on 2 fundamental. So we actually looked at, one second. So we looked at started with a very small piece of fluid or material, and by the help of we took help of 2 things, fundamental things, Newton's second law. So we took the help of this Newton's second law, and then with the help of simple mass conservation, we tried to in the last 2 days we tried to derive in a fluid or in a medium where the sound is propagating, how the particle velocity is going to be dependent on time and space. So this was our, all the maths, whatever we did was with the goal of coming up with a relation. And of course, there are certain assumptions that we made. And we said that yes, those are approximations, but it's a fair approximation to make in the context of the kind of analysis we are interested in the subject. We are not going into a higher level of analysis and the variations occurring because of the approximations, right? So with that we derived that okay, the particle velocity will have a function like this, and also we said that look, the velocity of sound in the medium is dependent on the fundamental fluid properties, and which we actually kind of derived from this equation itself, right? From the with the help of 2 equations, Newton's second law and the mass change in the, or rather the conservation of mass. If we look at from a small, delta kind of, small volume of fluid, from these 2 equations, we said that this is how the waves are going to behave. And then also we said that okay, these are some fundamental relations that we have between pressure and displacement. We didn't derive this because I said then we will the direction of the course will change. So from that, what we derived, we showed that even the displacement also has a sinusoidal kind of a behavior. So all the 3 things that we are interested in, the pressure, the velocity, as well as the displacement, all have a sinusoidal kind of a nature. And then the fundamental relations, we looked at the fundamental relations between the speed of the wave and then things like pressure, or the Young's modulus or bulk modulus rather in fluids, and Young's modulus in the case of a solid. We said that this is how the speed of the wave will be related to the property of the fluid or the material, right? And then we also came to the acoustic impedance. And here again, this equation we didn't derive as such, but then it is kind of easy to understand why the acoustic impedance should look like this. And we said that pressure can be like, it can be treated as synonymous to the voltage, right, or the potential, and the velocity of propagation of the wave can be thought of synonymous as current, right? And if we, and these equations or these relations we found out in the very first slide of trying to derive how the wave nature would be. So from that, what we said is, the acoustic impedance also is a function of the basic physical property of the fluid, and which again makes sense. Just that the reason we do the math so that we kind of understand, what kind of a function it is going to be like, right? And why are we even talking of impedance? And why are we trying to draw an analogy in the electrical world? Because only then we can make, let's say, electrical equivalent. We can study it in electrical terms, right? And then of course we can develop the electronics around it. So the intensity or the power density we said is nothing but the power dissipated or power incident on a given area. And then we did some little bit of maths here. We just added, or rather multiplied time on both sides. So power became work, and area and time, we left a product like this here. And then by using, these kind of steps, we said that, okay, the power density is nothing but pressure into velocity, which again makes sense because pressure, as we said, is equivalent to, let's say, the voltage, and the velocity is nothing but equivalent to current. So from that point of view, the intensity or the power density also we can make a sense out of that in electrical terms. So the power density or the intensity we wrote in, using these equations, which again look very similar to V square by R, or V into I, or I square R, right? And then what we said is, look, while we talk of power, at a given point, it is not going to remain constant as the wave propagates in space. So the power or the intensity is going to vary as the wave is propagating through space. Unlike, let's say, we don't talk of space when we talk of electrical, signals, right? We just talk of in terms of voltage, current. There is no space associated with it, right? So that is one difference that we have when compared to electrical kind of analysis. So we say that there will be an exponential decay in the power as of the sound wave or the intensity of the sound wave as it propagates through space. And we said that, okay, alpha W is what we will call as the power attenuation coefficient. And then we said that, look, now if a wave is incident on on an interface between two surfaces, surface 1 and surface 2, each one of them has characteristic behavior of C1 and R1, right, or C2 and R2, where C is nothing but the speed of the sound wave in that material, and R1 and R2 are the impedances, acoustic impedances. We are going to look at how C1, R1, and C2, R2 is going to decide theta I, theta R, or theta T. And we also said the reflection coefficient alpha R we will define as the intensity or the power intensity reflected, or the energy reflected at the interface divided by the energy that is incident on the interface. So that is energy reflection coefficient. And similarly, in the same token, we said the energy transmission coefficient will be the energy that is transmitted in the next medium versus the incident wave. And this is one law which I just introduced here, and I said that we'll derive this the subsequent slides. And alpha R also I showed you here, and that also we said that we will derive this equation, how it is coming. But this is easy to understand, that the intensity of the reflected wave and the intensity of the transmitted wave will be equal to the intensity of the incident wave, right? And based on that, alpha r plus alpha t, we can say that this equation will be valid. Alpha r plus alpha t will be equal to 1. And that, we discussed why it will be 1. If we add these two, and we know that the incident, the total energy, right? Of course, either it will be reflected or it will be transmitted. We are not talking of any energy that will be absorbed by the medium. That is one assumption that we are doing, but that's a safe assumption to make here, right? Okay, and then we said that look, since the displacement is a sine function, we can represent the displacement of the particle at any point in space x by a complex notation, right? Because complex notation has a lot of advantages, right? We know even in electrical circuits, we deal with complex numbers to help us deal with different kinds of impedances, right? Be it resistor or a capacitor or an inductor, right? So it makes sense to, and since we are talking of making an electrical network out of the medium, it makes sense to actually denote the displacement in complex terms, right? And because the displacement is having this kind of a nature, we can easily say that it will have this relation. If we differentiate it twice, we can easily show that this is what, there is no derivation here as such, right? If you just do the differential twice, you will end up with this, right? And then, so this is where we will start actually today's discussion, that which we left yesterday, that when the incident wave, and this is important to understand, the wave equations that we derived was assuming that the wave is propagating in a unidirectional manner, right, along one particular axis. So the wave is propagating in this axis, right? However, if we have to understand what kind of a behavior the reflected wave or the transmitted wave is going to exhibit because of the transmission, and because of the presence of the interface of two mediums, right? And both the mediums have different characteristics. The reference medium has rho and C as characterizing characteristic to the property of it, and the medium one, of course, is rho 1 and C1 as a characteristic of the of medium 1, right? So then what we are saying, one important thing to note here is, because the wave is incident, in these angles, right, incident and then getting reflected or transmitted, the velocity also we are denoting, in the same direction as the incident, as the wave is propagating, right? However, the pressure, when we are talking of the pressure exerted by these waves, corresponding waves, the pressure will be normal to the surface, right? The pressure in this case, there will be no direction of the pressure. When we are talking of the pressure will be normal to the surface. So we are showing the pressure, as in 90 degrees to the interface of the surface, right? So what I have done here is a very simple thing. The pressure equation that we had derived in the previous foils, we have derived it in the propagation, assuming that the x-axis is in the direction of the propagation of the wave. However, here in this case, the relationship that we are trying to derive is with respect to the interface of the two mediums, and hence the equation of the pressure wave, I am just modifying whatever x was there, right? So if you see here, so if this was my x-axis earlier, and now my new reference is this z and this x-axis, like I have shown here, then the same equation can be written like this. Now the question you can say, oh, sir, why are you not writing this omega t? The reason I'm not writing e to the power of minus omega t here as an additional thing, because omega t, we will say that it's there in all the subsequent equation, and there's no point in writing e to the power omega t again and again, right? So the pressure incident can be related. If I write the pressure equation, what I have done is I've just changed the x reference axis, what we had assumed, in the way that I have shown. Any questions here? No questions, right? We also had this equation earlier, which we didn't derive, and I said that you guys will have to trust me that this equation, the relation holds true. And actually, even if you look at textbooks in instrumentation engineering, they will also not derive this. They will just say that this relation is there, because as I said, then the subject becomes too diverse. So we have to fall back on our friends in physics department and have some trust in them and say that, okay, I mean, whatever they are saying must be true, right? So the relation between the pressure and the displacement is given by this displacement of the particle at that point. Please understand, this is pressure at a particular point. This is displacement of the particle at that same particular point, right? Is related by this equation. So from this, if I write, so what is pi? Pi we have written like this. So phi I, if you integrate with respect to time, we will get this. Or conversely, what you can do, if you put this equation phi I, if you put it here, you will see this is actually P, right? So you can see this d phi dt if you do omega t, right? So what we will get is divided by omega. If we differentiate this, right, omega will come into picture, this minus sign will come into picture, and of course there is an I that will come into picture. So if you just replace this equation here, you will see this holds true. So phi I also, just like, because I have shifted the x-axis now, what I have done is I'm trying to derive that this is my pressure equation and this is how the displacement equation is going to look like. Any questions up to this point, guys? This is understood, right? Okay. So what we will say is the pressure that is coming due to the reflection of the wave will be the pressure that is applied because of the incident wave, except that there is an additional component. I mean, we are multiplying this with a coefficient, reflection coefficient of Rp, reflection coefficient of Rp. What are the reason again I have chosen this notation as Rp, because this is the reflection coefficient in terms of pressure. This is not the same, please note, this is not the same as alpha that we because that alpha that we discussed here, this is energy transmission coefficient. This is energy, not pressure, not displacement, right? So here, in the next slide, what we are discussing is the pressure coefficient. I mean, the pressure happening because of the reflected wave is multiplied with the. I mean, it has a coefficient. It is going to be, a function of, it is going to be related to the pressure that is happening because of the incident wave, just that there is a coefficient coming into picture here. And please note another thing. Can you, another question, is there any other question that comes to your mind when you look at this equation other than RT? Any other question, guys, when you look at this equation? Look at this and look at this. So the question that can come to your mind is why this minus has become plus, right? So that again you can see because the reflected wave has kind of gotten back from this direction to this direction, right? So by the same logic of transforming the coordinate from x-axis in this direction to like having an x-axis in this direction, it is becoming x sine theta plus z sine theta, right? So this is the only big thing here. Otherwise, there is nothing much, right? Okay. So then, what is the total pressure that is incident on the interface? One is because of pi, the incident wave, and the other is because of the reflected wave. So I can write. I've just whatever we have derived in the earlier slide. I've just algebraically added them, right? Not a big deal. And as again, I keep repeating, Rp is the reflection coefficient in terms of pressure. And similarly, the overall displacement is, I I mean, the equation that we derived between phi and the pressure, right? In the same token, just like I have written it here, the overall displacement is again a sum of these two quantities, right? Any questions? It's the same stuff, right? Whatever we derived, we showed the differential thing in the previous slide. So the displacement is this, right? Now in the lower medium, where z is less than 0, in the way we have defined the axis, right? The pressure P1 is given by, again, the same quantity here, x sine theta 1 minus z cos theta 1 multiplied by a coefficient Tp. And why is this coefficient Tp? Because this is the coefficient related to the transmitted wave. So T stands for the to show that the wave that is transmitted, and P because we are dealing with pressure here, right? We are talking of the pressure that is of the wave exerted, the pressure exerted by the transmitted wave. Hence we bring in a new coefficient Tp here, and similarly by the same token the displacement equation in medium 1 will be given by this, right? Now if you look along the interface, right, when z is equal to 0, we had this interface, right? The wave is incident like this, and then it is getting reflected. This is my x-axis, and this is my z-axis, right? So along this interface, when z is equal to 0, we can write Pi plus Pr equal to P1. If you remember the diagram that I showed, that the pressure which is normal to the surface is Pi, this is Pr, and this is P1, right? So we can write like this, right? Pi plus Pr is equal to P1, just pressure balance equation, right? And if we do that, if I do Pi plus Pr is equal to P1, if I write this equation, then we can come up with a nice relation. What we see is, if if you look at it from equating the real component and the imaginary component on both sides of the equation, we come up with this expression k sine theta will be equal to k1 sine theta 1. So please note what we are doing. We are simply equating the imaginary component on both the sides. If we equate that, then we can write like this, which means sine theta by sine theta 1. So this is the equation which I had promised in the earlier slide that we will derive. So this is nothing but Snell's law. So this is a famous law this is called Snell's law. If you want to read more about this, but this is the basics of the derivation of Snell's law without getting into too much of the physics of the material, right? So this is a very important relation. Key thing to note here is the frequency. When we talk of the frequency of the sound wave, that is not changing. Please note that, right? Because if we look at this equation, whatever k was, this small k we had derived in the first slide, right? What was the small k, right? So sine theta 1 by sine theta by sine theta 1 is nothing but, if you go back to the let's go back to what was k for us, right? In the previous slides. So what was k? So this was our k, if you remember, when we derived the potential, the equation for the velocity as a wave, right? So this was what we showed our k as, right? K was nothing but 2 pi by lambda or omega L by CL, right? So if we remember that, and then now that we have derived from, whatever Snell showed, which will hold true for the waves, incident on a interface. The same equation, if I put it here, I land up with this kind of a relation. Only thing to note here is the frequency does not change, and also what we see is, if this holds true, this also must hold true. 1 plus Rp is equal to Tp. So if you see this P0 gets cancelled out here, and these components, if they are all equal, right? I can take these two guys common outside the bracket, and then I land up with 1 plus Rp on this side, and that I can equate it to Tp, right? So this is another important relation that we land up with, right? So now we'll proceed one more step further, and then probably we'll finish with our maths of looking at the wave equation. So the other thing that we will know is that the velocity. So read this carefully, assuming continuity in velocity normal to the interface. So when we are talking of particle motion, right, and we have an interface, from medium, let's say this is our reference medium, and this is medium 1, right? So when we look at the continuity in velocity normal to the interface, meaning this velocity, when we are talking of this velocity component, right, of the particles in these two mediums because of the wave, right, we can write ui cos theta. What was our theta? So this was our theta, right? Ui cos theta. So this was our incident wave and this was our reflected wave. So ui cos theta minus ur cos theta, because this is reflected, will be equal to, so this was our transmitted wave, right? And this was theta 1, will be equal to u1 cos theta 1, right? And of course we had this, that this is what was our acoustic impedance was. I just have rearranged U and written it in terms of pressure and the speed and the density of the material. So that means UI, if I look at this, only this component here, UI, I can write like this. UR is nothing but the same component multiplied by the reflection coefficient of pressure again, right? Because it's the same equation that we are writing. If you look at the amplitude, I mean the relation between the pressure wave function, the velocity wave function, or the displacement wave function, you will see it's the same coefficients are going to be applied in each of those equations, right? So the amplitude of the reflected wave can be given by whatever is the incident wave multiplied by this coefficient Rp, right? And of course, then we have U1 by the same token. We have U1, the wave that is getting transmitted. That I'm multiplying it by Tp. It's the same, same amplitude, just that a coefficient is getting multiplied. If I put all of these three into this equation, if I do that, what do I land up with? What I land up with is a nice relation like this: 1 plus 1 minus Rp is equals rho k1 times cos theta 1 divided by rho 1 k cos theta 1 Tp, right? So this gives me the second. We already had one relation, right, between relating Rp and Tp. In the previous slide, we already had a relation relating Rp and Tp, which was 1 plus Rp is equal to Tp. Now, if we have to find what is Rp and what is Tp, we need another relation. So, which is given by assuming the continuity in velocity normal to the surface. So, the second relation I land up with between Rp and Tp is given by this, right? So, from the first relation of 1 plus Rp is equal to Tp, and this guy, this relation that I found out here by assuming continuity in velocity normal to the surface, from these two equations, I can come up with the transmission coefficient of pressure. Again, I keep repeating Tp and Rp in these terms. Here, if you look at the equation carefully, rho 1 is again the density of the material. K again is dependent on the fundamental physical property. Theta, of course, we know because we know at what angle the wave is going to be incident and at what angle the wave is going to be transmitted, right? So basically we have been able to find out Tp and Rp, in fundamental terms, right? There is nothing unknown here anymore. And if I simplify this, further, then I can represent Tp as this. If you see, it's actually one and the same thing. It's just that I've gone one step further and replaced this K with k in terms of the velocity. It's the same equation, right? And similarly rp again. So basically these two equations are same, just that I have replaced k and formed. I've kind of taken away k and rewriting the coefficient in terms of the density and the speed of the sound wave in that medium, right? Okay, so now simplifying this a little bit more, if theta is equal to theta 1 is equal to 0, meaning the incident wave is normal to the surface, right? If you saw, this was our theta, right? So this was our theta. So if the incident wave is falling perpendicularly to the surface, if theta is equal to theta 1 equal to 0, then Rp becomes this. Why Rp becomes this? Because if you replace, so all these guys will become 1, and rho 1 C1, if you see the acoustic impedance that we have here, one second. So this R1 and R is nothing but the acoustic impedances of these, of these two particles. Of these two mediums, right? So Rp becomes R1 minus R divided by R1 plus R. So how do we now relate? Why did we do all this RP and all that stuff? Because actually we are interested in alpha R, the energy that will be actually reflected. Finally, we want to deal with also the power of the reflected wave, right? So alpha R is nothing but Rp square, because if we have a coefficient Rp in the pressure domain or in the voltage domain, in the power domain, the same coefficient is square of that, right? So alpha R becomes square of this. And going by that relation that we had, that alpha t plus alpha r was 1. So from that relation that we had, we have got alpha t as a function of these two acoustic impedances of these two materials. So now we have alpha t, alpha r, and that was, and also we have TP and RP. So this was the goal of the, all these maths that we did. So what all things we achieved by in doing all these maths? Number one, what we showed is how the pressure, the velocity u, and the displacement phi is a function of omega L, right? The frequency of the longitudinal wave that is propagating. It's a function of time and space x. So that is one thing that we got to know. Second, what we also got to know is what will be the relation between the incident angle theta and the transmitted angle theta 1 in terms of function of C1, C or C1, right? Right? Or K or K1, or K or K1, right? So this we derived, right? And third, what we got to know is, of course, how these pressure coefficients are related to each other. We got to know the relation between TP and RP. And also we got to know how the transmission coefficient of power, the energy transmission coefficient and the energy reflected coefficient of energy, right? That is related to TP and RP. So these four things we kind of achieved in doing all the maths. Any question here up to this point? And please hold on, once we go into the electronics portion, you will see how these equations are going to be used. Any questions up to this point? Otherwise, we will proceed further to, we did some kind of maths the last few foils, and quite a bit of it we kind of left it to the physics folks, and we tried our best to kind of come up with a relation between the fundamental wave nature. Any question that comes to you guys, Shubham, Ayush? Okay. Don't have any questions, so now let's go back to the electronics portion of it, right? So what we have in the ultrasound is essentially we have a transmitter and a receiver of sound waves. So we will be transmitting sound waves and the sound wave will be reflected. So in one case I have shown here is a flat target, and as you can see visually, if it's a flat target, the reflection will probably the best, will happen probably the best, right? The reflection coefficient will be probably the best. Alpha, I mean here RP will probably be the highest in this kind of a scenario, right? If it's a round target, then we see that the waves are getting scattered, and the the intensity of the reflected wave received by this receiver will not be as much. It will be smaller because it is getting scattered, and this is actually again a tilted target. So the point that I am trying to highlight here is based on the position of the target. It is not only based on the on the fluid characteristics of this medium, but also in our previous equations that we derived, we assume that there is no shape. I mean, we assume that it's a flat interface, right? But if it is not, if the interface is not flat, or if it's at an angle, then of course the energy that will be reflected back to the receiver will also be a function of the shape of the target, right? So similarly, the reflection coefficient example. So for example, when we are talking of let's say medical devices, right? We have a transducer here, and we give the sound wave pulses, and we have, let's say, something like skin. What we can see here is, because this medium is air, and this medium is skin, most of the waves are reflected back, and only 1% is transmitted. So what does that tell us about the acoustic impedance of this medium and this medium? So this is, let's say, my reference medium, and this is my medium 1. So now that most of the energy is getting reflected back, what does that tell us about the relative impedances of these two mediums? Are they very similar or are they very different? If most of the thing is most of the energy is reflected back, what does that tell? That this RP has to be very high, right? If RP has to be very high, that means R1 minus R, these two are pretty different from each other, right? So the acoustic impedances of medium 1 and the reference medium, these two are quite different from each other, and hence most of the waves are getting reflected from the skin, right? Yes or no? And if most of the waves are getting reflected back, only 1% is entering the skin, right? The same thing I have shown with respect to water and steel. So here you can see 88% of the waves are getting reflected back. Key thing to note here, any question that comes from this diagram that I have not explained, if you see here, right, this portion I didn't talk about, right? Which means if you see there is some portion of the wave is actually entering the medium 1, and here there is another interface, right, from steel to water. Here we have water to steel, right? Here we have water to steel, and here we have steel to water. So the portion of the wave which is actually getting transmitted, some portion of that is again getting reflected back from this interface. And then from this wave, some portion is further getting, it's going back into the water. And at this interface again, some portion of it gets back again, right? So this kind of tells us that we have to, whenever we are designing the electronics, we have to be careful of taking into consideration all the interfaces that might come into picture, because when we are going to actually receive in the receiver mode, right, we will be not only receiving this guy, but also we will receive this guy, right? Or if we have the receiver somewhere sitting here, we need to know that, okay, most of the, or what portion of the energy would have actually gotten, it stays in this medium, right? So please understand this. Any question that comes to this diagram, from this diagram? And what story these numbers tell us between the relative impedances, acoustic impedances of these two material? That please go back to, if you go back to the equations that we derived. So this again is the energy transmission coefficient. This is energy reflection coefficient. This is a function of the acoustic impedances of the two mediums shown by this, right? And this is the reflection coefficient of pressure wave that is related to the acoustic impedances given by this. And TP, of course, I don't think I've shown. RP is this, and we had a relation. What relation? I mean, I have not shown here. I think purposely I have not shown what is TP. If RP is this, you can find out what is TP when theta is 0, right? When theta is 0, RP, so this equation we have, right? So from this you can find out what will be RP, right? So this diagram tells us what, what is the like relative acoustic impedances, and based on that, how much energy will be reflected back or how much energy will be transmitted. Okay, so now that we have done all that, we have to now get back to modeling of two-port network of the transmitter, right? And only then we will be able to make the electrical equivalent circuit, right? So let's look at, yes, Ayush?
With energy, do we actually mean that the amplitude is changing, being frequency is constant for a particular medium?
I couldn't get your question. Can you be louder, please?
Sir, I was asking that as you are saying that energy is being 13% in skin or something, you mean that the frequency being constant, the amplitude is decreasing?
Yes, correct. That's what Snell's law told us, right? If you see the frequency, if you see the Snell's law, right? If you look at this, right, the fact that we equated these guys, sine theta and sine theta 1, right? So we had k here coming into picture. X is anyway x, and it's just space, right? So x gets cancelled out. So what did we have here? We had k sine, I mean, if I again rearrange this term, right? Let me, so we had P0 e to the power I kx sine theta, right, multiplied by 1 plus rp is equal to tp p0 e to the power I k sine theta k1 sine theta 1, right? So p0 gets cancelled, and if we were to equate these two portions, we land up with k sine theta is equal to k1 sine theta, and we know what is k, the wave number, 2 pi by lambda, or that was also equal to omega by c, right? So if sine theta by sine theta 1 is nothing but k1 by k, right? So which means lambda by lambda 1, right? So if you, so from the basic wave equation, what we have is c is equal to f lambda, right? So here, if c by c1 is equal to, so c equal to f lambda, this equation we have, right? For any wave, plane wave, this will be valid, right? Any question? This is a famous equation, right?
Yes, sir.
Yeah. So this I think you know from class 12 physics, right? So if c by c1 is equal to k by k1, and if I replace, which means lambda by lambda 1, that means what are we saying here? That the frequency of the wave remains the same in the two medium. Frequency doesn't change. That's what we are kind of saying. What we are also saying is that depending on these impedance, the characteristic, the acoustic impedance of the medium. So what we did was, important thing to note is the energy coefficient, the relation of the energy coefficient. So one important thing is this itself, right? How the energy reflection coefficient is related to the reflection coefficient of the pressure, right? And also we know that the transmission coefficient is 1 minus alpha r. So Rp if we derive, alpha t we can, alpha r if we can derive, alpha t we can derive from here. And from that diagram, what it tells us, if most of the energy is reflected back, that means the acoustic impedance of these two materials or the fluids are quite different from each other. And that is the reason, if you, and I will discuss this more once again. See, if you remember, have you seen a doctor doing an ultrasound on a patient? So he has a handheld kind of a device which he rotates around the skin of the patient, right? But before he does that, he applies a gel. You know that, right? Have you seen that? Have you seen any ultrasound being done?
Yes, sir. Yes.
Yes. And why is that gel needed? So the gel actually, so I'll discuss that in the subsequent foils. The gel, yeah, here, I'll come back to that again once, we go into the, two-port network and we derive, you will see that, okay, so the gel is needed as an interface to ensure that if I have a medium here like this, right, is we can have, our goal is this when we are doing ultrasound, right? So let's say on the other side of the skin, what will we have? We'll have blood, right? So now if 99% of the energy is getting reflected, it is not even going into the blood. How will we even study the, the body, right? Which is under the skin, right? So we need to ensure that most of the energy should enter the skin. To do that, we actually have a gel which will ensure the relative impedance between air and the gel and the skin will be such that maximum portion of the energy will get transmitted, and we can actually derive an equation for that, which I will show you what will be the acoustic impedance to ensure that much of it is actually getting transmitted, right? We'll discuss that again. Any more questions on this? I actually don't want to get into this TX RX portion in this class because this is actually a logical point to stop. But I think I labored through all the maths with you people to just explain, as I said, I keep repeating, why did we do all that? Is to show the sinusoidal behavior, right? Sinusoidal behavior of pressure, velocity and displacement. That is number one that we saw. Second, we talked about impedance, right? Acoustic impedance. As a function of the basic fluid properties. Third, what we discussed is how alpha R and alpha P is related to the acoustic impedance, function of R1. And similarly, fourth, which is very similar to the third one, is how TP, the transmission coefficient of pressure, or RP, the reflection coefficient of pressure, is related to acoustic impedances, right? So this is energy coefficient and this is the pressure coefficient, which is actually, because P, U and phi, they're all kind of related to each other. These same coefficients will also appear when we talk of velocity or displacement. These coefficients will appear here. These coefficients will also appear, but with a square term, right? So this is what we kind of, our net takeaway from doing all the maths was this. So is this clear? I'm trying my best to, cover. This is actually, that's why this subject becomes a little bit difficult to kind of make it interesting all throughout. because we as electrical engineers, the moment I think we come to physics, we kind of lose our interest, right? Because it becomes too much of physical maths, which we don't deal with, right? We want to look at electrical equations, which we will do. But the reason why we had to do all this stuff is to understand, so for example, if you are designing an ultrasound, right, it's very important to understand how much energy is actually going to be reflected. Only then we can do a model, right? We have to have a model for this interface. We need to have a model for this interface, right? So we can do an electrical model only if we understand, how the electrical characteristics are going to be dependent on the physical characteristics. So we'll stop here today. Any questions, Shubham, Ayush, both of you? Yeah, Shubham, you are good? Any problem?
No, sir.
Okay, so then we will stop here for the day, and then we will start doing the two-port equivalent network of ultrasound in the next class. Thank you.